Assalamualaikum warahmatullahi wabarakatuh. And greetings, Doctor. So we are from Group 11, and we're going to present to you about our project, which is the Deadlock resource allocation graph, Deadlock Avoidance-Safety algorithm, and specifically bankers algorithm. So the Group 11 consists of 4 members, which is AZIZ bin MABENI, Ahmad FAIZ bin ALLAUDDIN, Muhammad HAFIZ bin KHAIRUL, and myself, HISYAMUDDin bin HAMZAH. So let's move on.
Hello, my name is Muhammad HAFIZ bin KAMAL, and I will be presenting the abstract, problem statement, future words, and conclusion. So for the abstract, the aim of this project is to create a program that uses the resource allocation graph, or RAG, to detect deadlock and the safety algorithm to quite it, both of which enhance the food delivery scheduling system. By presenting the data in terms of the diagram, RAG aids in the explanation of the system's state in terms of its resources and processes. So what are the problem statements? Deadlocks occur during peak hours. For instance, when it's 12 p.m. until 2 p.m., which is lunch hour, the system will have multiple delivery orders, which may cause deadlock. This is due to the fact that there are not enough delivery workers, which may cause delivery of the food item to be delayed. As time passes, the food may be less appetizing or not fit for human consumption. Food can get oily, soggy, stale, or form bacteria. Next, there will be a drop in standards of service. This is due to the fact that the scheduling system will have a hard time managing resources effectively when the number of customers and order rises. This can lead to a moment where no progress can be achieved, which may cause a decline in customer satisfaction and delivery efficiency. In order to avoid this, deadlock avoidance is necessary to reduce time-consuming delays and maintain high standards of service.
Hi, my name is FAIZ, and I'll be explaining about the methodology of this project. So first, we started our project by discussing the project, and then we distribute the task for each our respective members. After that, we prepare the project, and then we analyze the project requirement so that the project are being followed by through the rubric of the project. And then we prepare the application of the prototyping. Once that has finished, we test the prototype by 5 consecutive times, and then we prepare a report. Once the report has been finalized, we prepare the content of the presentation, and then once that has been done, we prepare the project presentation. So the hardware requirement so that this project can be run is that the processor, the minimum of the processor, which is the Intel Core i3 or AMD Ryzen 3 or even the latest processor. For the RAM, which is the 2 GB, and then for the CPU, 2 GHz, and then for the GPU, Intel HD graphics, AMD Radeon Vega or similar GPU card. And then so for the disk storage, you will need at least 1 GB of free disk space. So for the software requirement, so for the operating system, the minimum requirement for this project to be run is that you can use Windows XP or even newer. For the macOS product, you can use OS X v10.7 or even higher version. For the Linux, you can use the Ubuntu. So for the integrated development environment, which is IDE, you can use Microsoft Visual Studio Code to run the project. So the prototype testing. So in here, in the diagram show, the system correctly show the allocation, the maximum, and the need matrices in each tested case. And so as you can see in the table of the testing, these are the two testing of the results out of 5 testing that we have done on our project. All right, that's all. I'll be passing to my next friend.
Assalamualaikum and good evening. My name is ABDUL and I will be explaining for the design and implementation for this project. This project we implemented the bankers algorithm, which consists of the resource request algorithm and safety algorithm. So for the system flow, initially the program execute the input function where it asks the user for the keyboard input. First they ask for the number of resources in the operating system simulation, then they ask for the number of process. Then it asks for the matrices, which is for the available resources, maximum resources, and the resource allocation to initialize the operating system simulation. Then it proceeds to the matrix operations consists in the input function still. So the matrix operation will print the input matrices and calculate and print the need matrix for the allocated process and resources matrix. So next it will run a safety algorithm check for the initialized operating system resource and process. So it will print the result of the safety check. If any deadlock occurs, then it will notify the users of the unsafe state of the system, and if not, it will print the safe sequence of the initialized resource and processes. The user can proceed with the execution of menu function where it will print out the 5 operation and wait for the user's input to proceed with any operation. The first operation allows the user to add additional requests to a process and check using the resource request and safety algorithms. This is the main function of the resource request algorithm, the main implementation and simulation for the resource request algorithm, as it will simulate a request input by the user. Then it will check if the resource request is available to be implemented, to be pretend to implemented. Then it will check the safety of the system by the safety algorithm to check if this request is safe to be implemented or not. Operation 2, 3, and 4 is used to change the maximum resources, allocation resources, or the initial resources of the initially defined values of the matrices. And operation 5 will simply exit the system once we done with the simulation. After each operation, except operation 5, the menu will loop and will ask for the user input until the user input 5. If the user input other than 1, 2, 3, 4, 5, the system will print an error message, then ask the user for the input again. So we'll go through the main functions of the system. So firstly, the system first is the input where the user input the value of matrices and all of the resource and process allocation, maximum and available resources. Then it will print out the calculation and the need matrix. And then it will run the initial safety check for the system. Here is the table print algorithm where it calculates the work. Is one of the function in the input function where it calculate and print out the matrices. Next is the safety algorithm where which is the longest algorithm here, where it checks out the safety of the resource allocation maximum and available by comparing the need and work. If the need is less than or equal to the work, then the process is safe to be implemented in the sequence. Then it will print out the sequence for the system if they are in a safe state. If not, it will print out the error message, not the error message, the deadlock occurred message for the system. Next is the request resource where it asks it is implemented in the menu function where it asks the user to input a request for a process and check if the request is available to be implemented or not. Then we get the change maximum to change the maximum resources for the initialized operating system values, and You also got the change allocation and the change initial resource, which practically does the same thing, except for it change the.
So my name is HISYAMUDDIN, and I will be the one who's gonna present the results and discussion. So so as you can see here, the topics of our project is mainly on the Banker's algorithm. So the Banker's algorithm serves as a prevention algorithm to prevent the deadlock by determining the safe sequence for executing the process. That's hence our program is able to determine safe sequence for a set of processes and resources by implementing the Banker's algorithm into the code itself. So this demonstration is already demonstrated in the methodology part. So the next one is the discussion. So I will be showcasing the example of the scenario that we use. So as you can see here, there are five processes that we use to demonstrate our program. So as you can see here, the programs the scenario that we use. And then the steps. So Banker's algorithm mainly have three steps. Which is the first one is to set the work as available. Available is here the available resources, which is initially is 332 the matrix, and then we go to the next step, which is checking whether the need is less than equal to work. So the need is automatically calculated in the program also. There is a function specialized on that, which is formula for need is max minus its allocation. And then we're going to check one by one of the process whether or not it satisfies the conditions. And if it satisfies, then we'll go to the next step, just step 3. And as you can see here, need P1 is less than equal to work is false. It does not satisfy the condition. However, the need P2 is less than and equal to work satisfy the condition. So we go on to the next step, which is step 3, which is setting the new work. So as you can see here, the formula is work equal to work plus allocation of the process that satisfy the conditions in step 2. So since P2, process 2 will satisfy the condition, then we select the allocation P2, which is 200, plus with the initial work that we have earlier, which is 332. And then we get the new work, which is 532 in the form of matrix. And the process of the Banker's algorithm keeps continuing until all of the process has finished. So as you can see, the next step, we've gone back to the step 1, which is with the new work, and then step 2, we check again which process satisfies the conditions with the value of the new work that we have calculated before. And then as you can see here, need P3 does not satisfy the condition, and P4 satisfies the conditions. And then hence we select P4 to be executed, and then we update the work. And then the rest, this is the rest of the algorithm. And as you can see here, there is another 2 more iterations until the final iteration. And then after the final iteration, we can conclude that the safe sequence there to execute the process will be P2 first, and then followed by P4, P5, P1, and then P3 will be the last to be executed. Okay, so the next one, what if there is a request? So whenever there is a new request, we have to update the following variables first before executing the Banker's algorithm. So we have to execute the resource request algorithm to determine the new sequence. So it is just as simple as the formula, as you can see here, as I showcase here. So we just update 3 of the main variables, which is the available, allocation of the process that requests the new resource, and then the need, and the need of the process. So the calculation is pretty much simple, as you can see here. After we have updated all of this, then we can put it back into the table and update the table. As you can see here, there is a changes in the table, which is P2 because P2 requests for another resource. So after running back again the Banker's algorithm, we're gonna get a new safe sequence, which is P2 followed by P4, P5, P1, and P3. It's pretty much the same as before. So I think that's pretty much it. Thank you.
Future words and conclusion. First, let's talk about challenges and discoveries we found throughout this project. One major challenge we faced was the scarcity of practical applications that use safety algorithms to tackle deadlock problems. This gap highlights the need for innovative solutions in this area. We also realized that safety algorithm is crucial in scheduling systems, especially when dealing with hundreds of concurrent processes. These algorithms help maintain order and prevent system halts. Let's talk about the Banker's algorithm. The Banker's algorithm is designed to manage resource requests one at a time, ensuring that each request is safe before approval. This careful handling prevents unsafe states. Through this project, we gain a deeper understanding of deadlocks and the role of safety algorithms in preventing them. This knowledge is critical for developing efficient scheduling systems. Overall, this project has been instrumental in providing us with valuable insights into how safety algorithms can be used to resolve deadlock effectively. That is all, thank you.